Okay, today I want to talk to you about voltages and equipotential lines. Voltages we've already talked about, but this new thing is kind of tough. I was hoping to talk to you in person about this, but we don't have that option, so let's do our best. Okay, so first of all, if we have a charged object like a balloon, surrounding that balloon is going to be electric fields and voltages. Voltages go by a name that I never used with you yet, and that word is the word potential. Not potential energy, just the word potential. The reason is voltage is kind of a way of describing the potential to have potential energy. So if there's a voltage here, and then I place a charge at that spot, those charges will then have a potential energy stored between them. So I know it's a little bit confusing, but let's say here's my sensor, and let's say it measures 9 volts. That's 9 joules per coulomb. There's no actual energy there until I place a charge here. But there is a potential to have potential energy. So I hope that made sense. Let's make a more concrete example. Let's take a 200 nanocoulomb charge, place a sensor some distance away, in this case 1 meter, and we would calculate a voltage of 1776. Hopefully you remember that the equation looked like this: voltage, or potential, coulombs constant, charge, this is the charge, not the one you're placing there, but the one that was already there, and the distance we are from that charge. So we pick up a value for potential of 1776 joules per coulomb. That is in reference to when this sensor is infinitely far away, it would have no voltage. So to get from infinitely far to here is a change of 1776 joules per coulomb. Okay, let's try and make it a little more real. So first of all, we put our sensor in a different spot. We got almost the same answer, 1773 joules per coulomb. Look at where my sensor is. And this time what I want to have the sensor do is move to a new spot. And you'll see that when I move the sensor, I change the voltage. Really, the voltages themselves are not the important thing. What's important is how much did it change. So you're looking for how much did the voltage actually change when I went from place to place. That's going to be called potential difference. You'll notice I'm moving the sensor and not having any change in voltage, and that's because I'm moving in a circular path. All the points along that circle had the exact same voltage. You'll see now my voltage is going up as I move closer. That means I'm having more potential for stored energy. If I was actually moving a charge from here to here, and it was a positive charge, I would have been adding potential energy to that system. We did this earlier this year where we had our sensor at point A and our sensor at point B. We measured our voltage at each spot. And I told you these numbers are not the important thing. What's important is the difference between them. So in this case, we have a voltage between them of 60 volts. That will allow us to figure out how much energy we're going to gain or lose as we move a certain charge from point A to point B. So let's say I was moving an electron. I put the charge of the electron, I multiply by the change in voltage of 60, my coulombs cancel, and it tells me how much energy my electron gained or lost. Does it gain or does it lose? Well, then you have to think about what your charges actually are. So if that charge was positive, the electron would get pulled towards it, so I'd be losing potential energy and turning it into kinetic. If this was a positive charge and it moved from B to A, it would require me to do work, so I would be gaining potential energy as these two things are trying to shoot apart. To see it more concretely again, I take two positively charged objects. They're going to repel each other. I'm going to be moving from this point to this point, and you can see I am gaining kinetic energy, which means I'm losing potential energy. My voltage is decreasing. We could see the opposite, where we take our positive charge and we shoot it at our stationary charge. And in this case, you see it slowing down, slowing down. This time I'm losing kinetic, so I'm gaining potential. I'm gaining voltage as I move inward. My maximum voltage would have happened right there. And then that potential turns back into kinetic as it gets shot back away from the mutual repulsion between those positive charges. Okay, most of that was stuff we had done before. Today's really new thing are these things called equipotential lines. And hopefully you can figure out what they mean. Equi means equal. Potential, we learned, means voltage. So these are lines of constant voltage. So if you look, here's my charge. This is an equipotential line where everything on this purple line is 30 volts. Every spot along this blue line is 20 volts. And every spot along the red line is 10 volts. Equipotential. All the spots on that line are at the same voltage. There's a line for 10 volts, 20 volts, and 30 volts. I could put as many of these lines in as I want. I just don't want it to be too confusing. So sometimes fewer lines makes it easier to read. Okay, let's make a more concrete example. We have charge 1 is 10 nanocoulombs. Everywhere on this purple line is 40, 30, 20, and 10. And what you should realize is, again, that 40 and 30 are not that important. What's important is if I go from anywhere on there to anywhere on here, that's a change of 10 volts. If I go from, let's say, here to here, since they're both on the 20 volt line, that's a change of 0 volts, okay? It would take no energy to move along from X to X. If I went some other path where I actually left here and did crazy paths to get here, there'd be times where I'd be gaining energy and losing energy, but I'd end up with the exact same amount of energy that I started with. The path I take doesn't really matter. Here I just upped the charge to 20, and you'll see the circles got bigger. You'll see here I made the charge in the middle smaller, and the circles got smaller. Here is where things really become important. When you have multiple charges, your equipotential lines are no longer circles. They take on these strange shapes. And these strange shapes make it super easy, because if I had a third charge that I took from here, let's say, to here, and I wanted to know how much energy did it take to move from place to place, I could just say, well, I started at 10, I ended at 20, so it was a change of 10. 10 joules for every coulomb that I moved. You can also see that there are places where the lines are really close together. That means it's going to be really hard to move from place to place, because it's going to be a rapid change in energy. If the charges were attracting each other, then it would actually happen really quickly at those spots, because the lines are really close together. You can see where the lines are far apart. That means it does not take a lot of energy to go from here to here. Okay? So you're looking at the spacing of the lines and what these shapes look like. Think of these a lot like a topographic map. So if you were out hiking at, let's say, Big Cobbler Mountain, this is a topographic map that you might be able to get on your phone or pick up at the ranger station. And what this shows you is the elevation. This is exactly like equipotential lines. But these are not voltages, these are heights. So everywhere along this line is 800 feet above sea level. Everywhere on this line is 1,200 feet above sea level. If you go from this point to this point, you change by 100 feet. You went from the 800 to the 700. It doesn't matter what path you took, there is a net change of 100 feet. If you walk along this line, you would not be rising or falling in elevation. You'd be walking at a constant height. It would be nice and easy. If you walk perpendicular to these lines, that's the steepest that you're going to encounter. Where these things are really close together, it means the elevation is happening, the elevation change is happening really quickly, really, really steep. And where these lines are far apart, it's showing you that the ground there is almost flat. Okay? So closer together means steeper. Farther apart means flatter. The most difficult path is if you hike perpendicular to these lines, and the easiest path is if you walk along these lines. Here's another topographic map. This happens to be a volcano in Hawaii. It's Mauna Loa volcano, and you can see it actually has 4 different peaks of varying heights. You can see areas that are relatively flat and areas that are really, really steep. Okay? So when you look at your equipotentials, equal voltages, think of them like topographic maps. Where the lines are close together, rapid change in energy. Where the lines are far apart, the energy change is really mild as you move along the plane. Okay, so again, these are just some maps to look at. Here are a couple problems to try. How much energy would it take to move a proton from the red line to the purple line? Red to purple. Again, you don't care about the two numbers, you care about the difference. So find the difference in voltage between these two spots. That'll come out in joules per coulomb. Multiplied by the number of coulombs in a proton. That'll tell you how much energy to go from here to here for a proton. Then you want to know how fast the proton would be moving. So this time we're going to start on the purple line. We're going to move to the red line. You do the same darn thing. Find the volts, subtract, get the potential difference. Multiply by the charge of the proton. That gives you again the energy change. In this case, we're losing potential, so we're gaining kinetic. So whatever you get, plug it into your kinetic energy formula and solve for velocity. I hope you can visualize these just like topographic maps. I hope you can easily use what these maps are showing us. Anyway, if you have any questions, please email me and let me know.